Are we looking at the whole picture? We gaze out into the deep black of night. We see stars. We see galaxies spiraling in silent, majestic dances. We see the faint, ancient light from the dawn of time itself. Our telescopes are powerful. Our theories are elegant. We once thought the Earth was the center of everything. Then we learned it was a planet orbiting a star. Then we learned our star was just one of hundreds of billions in a single galaxy. Then we learned our galaxy was one of trillions in an observable universe. Each step revealed a grander, more humbling reality. We are now standing at the edge of another, perhaps the greatest, curtain. The data coming back from our most sensitive instruments tells a strange and unsettling story. The universe we know, the one made of atoms, stars, and planets, seems to be a minor detail in a much larger, darker, and more mysterious cosmic drama. We map the cosmos with light. We see the brilliant glow of a nebula where new stars are being born. We detect the faint residual heat of the Big Bang, an echo from 13.8 billion years ago. We measure the stately rotation of galaxies, their arms swirling like cosmic pinwheels. But the numbers do not add up. The motions we observe cannot be explained by the matter we can see. It is as if an unseen hand is guiding the stars. An invisible force is pushing the galaxies apart. Something profound is missing from our inventory of the universe, and its absence is the single greatest mystery in all of science. We are adrift in a sea of unknowns, and the map we hold is almost entirely blank. This essay is about the blank spaces on that map. It is about the ghosts in the cosmic machine. The first great mystery is a substance we call dark matter. We give it a name not because we know what it is, but because we know what it does. Imagine watching a merry-go-round spin. The horses on the outer edge move slower than the horses closer to the center. This is a basic law of rotation. We expect galaxies to behave the same way. Stars far from the galactic center should orbit more slowly than stars closer to the dense, bright core. This is what gravity predicts. But this is not what we observe. Instead, we find that stars on the outermost edges of galaxies are moving just as fast, and sometimes even faster, than stars much closer in. This observation is a profound violation of our understanding of gravity. There is only one logical conclusion. There must be more mass present than what we can see. A lot more. This unseen mass provides the extra gravitational pull needed to hold these fast-moving stars in their orbits, preventing them from being flung out into the void of intergalactic space. This mysterious, invisible stuff is dark matter. It does not shine. It does not emit light or heat or any form of radiation that our telescopes can detect. It seems to pass through ordinary matter like you and me, as if we were not even here. The evidence for its existence is overwhelming, yet its nature remains a complete enigma. We see its gravitational effects everywhere we look, within galaxies and in the buzzing motion of clusters. We see its signature in the way light is bent, gravitational lensing. Dark matter acts as an invisible lens, distorting the images of galaxies behind it. All the stars, planets, gas, and dust, everything made of atoms, accounts for only about 5% of the total mass and energy. Dark matter makes up about 27%. It is the invisible scaffolding upon which galaxies are built. So what is it? That is the billion-dollar question. Scientists have proposed many candidates. Perhaps undiscovered particles, heavy and slow-moving, forged in the heat of the Big Bang. These are nicknamed WIMPs, or weakly interacting massive particles. Or perhaps a tiny ghost-like particle called an axion. It could even be a sign that our theory of gravity, Einstein's general relativity, needs modification on cosmic scales. We have mapped the ghost's shadow across the entire universe. We have weighed it, but we have never seen its face. It is a fundamental component of our cosmos, and it is a complete mystery. How do you search for something that is invisible and interacts with almost nothing? Scientists are tackling this challenge with immense creativity and powerful technology. One approach is direct detection. Deep underground, laboratories are filled with ultra-sensitive detectors, often containing purified liquid xenon or supercooled crystals designed to wait patiently. The hope is that a dark matter particle collides with a nucleus, creating a tiny flash or a vibration that can be recorded. So far, these silent vigils have yielded nothing conclusive, but the search continues with ever-increasing sensitivity. Another method is indirect detection. If dark matter is its own antiparticle, annihilations should occur in dense regions like the galactic center, producing gamma rays or neutrinos that our telescopes can see. So astronomers point instruments like Fermi toward the core, searching for an excess beyond known sources. Finding such a signal would be a smoking gun. Finally, there is the method of creation. At the Large Hadron Collider, we recreate conditions moments after the Big Bang. The goal: create new, undiscovered particles among the debris. If forged in the lab, we could study their mass, spin, and interactions. Detectors look for missing energy, signs an invisible particle flew away. Direct detection, indirect detection, and creation form a coordinated worldwide effort. A hunt for a new piece of reality that could open a new window on the universe. The second mystery is perhaps even more baffling than the first. For most of the 20th century, cosmologists asked, what is the ultimate fate of the universe? The consensus: two possibilities, both governed by gravity. If there was enough matter, expansion would halt and reverse, the Big Crunch. If not, the universe would expand forever, slowing like a ball that never falls back down. Two teams used distant supernovae, standard candles, to track expansion history. What they found was the exact opposite. The expansion is speeding up, a discovery that won the 2011 Nobel Prize in Physics. Something pushes space-time apart. We call it dark energy. Not starlight or heat, but a property of empty space itself, growing as more space is created. About 68% dark energy, 27% dark matter, less than 5% ordinary matter. Dark matter pulls, dark energy pushes. Right now, dark energy is winning. The universe is running away. Understanding the nature of dark energy is one of the primary goals of modern cosmology. Since it is a property of space itself, we cannot capture it in a lab. We must observe its effect on the largest scales. Massive surveys like DES and the Legacy Survey of Space and Time map millions of galaxies across billions of light years. By charting expansion history, we can test ideas about what dark energy might be. Is it Einstein's cosmological constant, uniform and constant, or a dynamic field, quintessence, changing over time? The cosmic microwave background carries early universe imprints shaped by dark matter, ordinary matter, and dark energy. Analyzing these patterns reveals how dark energy influenced structure over 13,800 million years. Cosmic archaeology. If constant acceleration continues, galaxies drift beyond the horizon, ending in a cold, lonely big freeze. In some models, a big rip. Understanding dark energy is about understanding our cosmic destiny, the final chapter still being written. The third great mystery takes us to the very edge of existence. Our story begins with the Big Bang, about 13,800 million years ago. Unimaginably hot and dense, compressed into a point, then expanding, cooling, and evolving into the cosmos we see today. The Big Bang explains expansion, the microwave background, and light element abundances. Yet, it has a critical limitation. It tells us nothing about the moment itself, or what, if anything, came before. Since space and time begin there, asking before may be like asking what is north of the North Pole. Some theories suggest eternal inflation, our Big Bang as one bubble in an ever-expanding multiverse. Others imagine universes born from black hole singularities in a larger parent reality, cosmic natural selection. To truly answer, we need a unified theory, quantum gravity, to bridge general relativity and quantum mechanics. Such a theory may finally describe the birth of space and time and yield testable clues about what came before the beginning. So, are we looking at the whole picture? The evidence overwhelmingly suggests we are not. We stand on a small island of understanding, surrounded by a vast ocean of ignorance. Atoms are a cosmic afterthought. Dark matter holds galaxies together. Dark energy pushes them apart. We traced our origins to a fiery singularity, yet the ultimate beginning remains shrouded. These are not failures of science. They are its greatest triumphs, revealing depth and a boundless frontier. Each answer opens deeper questions. Curiosity drives the search for dark matter, the mapping of dark energy, and a theory of quantum gravity. We look up and wonder. We do not know what we do not know. The cosmos is vast, and our journey has just begun. If this video sparked your curiosity, support the channel with a like and comment, and subscribe to Last Minute Space for more unexplained wonders of the universe.